Welcome back to the Code Navigators, your essential guide to conquering the complexity of building standards. We're here to help transform those pretty daunting ICC code books, page by page, into clear, actionable, and navigable maps.
That is absolutely our mission. This specific content review, it's really designed to walk you through the International Code Council codebooks, chapter by chapter. We explain the core contents and, maybe most importantly for those preparing for certification, we detail the most efficient ways to find information quickly.
Yeah, time is everything during an exam, isn't it?
It really is. And knowing the organizational logic of these chapters, that's the ultimate shortcut.
And just for full production transparency, as we navigate this pretty comprehensive material, you should know that this content is the result of AI-assisted generation. But it's produced and carefully overseen by a human code professional.
Right. We're trying to combine efficiency with technical accuracy, making sure we hit the right topics with the right context.
Okay, but before we dive in, we have to do the important legal bit.
Absolutely crucial. So let's be very clear. This information is provided strictly for educational purposes only.
Right. Not professional advice.
Exactly. It's not intended as professional advice or design guidance or, engineering interpretation. You, the listener, you must always consult the official current ICC codebook.
And a qualified professional.
And a qualified professional for any specific projects, interpretations, or actual construction decisions. And we won't be stating any copyrighted material. Everything we discuss is based just on the concepts and the structure of the public domain source material we've reviewed.
We're helping you study the map,
Yeah.
not build the actual structure.
Precisely.
Okay, so today we are tackling a foundational pillar of life safety in construction. The 2021 International Building Code, Chapter 7. This is the big one, covering fire and smoke protection features.
Oh yeah, Chapter 7's huge. It's where building design gets really complex, moving from just structure to compartmentalization. It governs everything. I mean everything, from how long a wall needs to stand up in a fire.
And how you poke a duck through a floor safely.
Exactly. So our navigational mission today is to cut through all that density and give you those critical mental markers. We want you to know, quickly, if you need a firewall rating, where do you jump? If you need to know, say, the max size of a window near a property line, where's the go-to table?
Okay, let's unpack this chapter then,
Okay.
starting right at the beginning. Section 701, General. Seems pretty straightforward, but what's the fundamental philosophy here laid out in 701.1? What's the core idea of the whole chapter?
Well, 701.1 defines the main purpose, and it's important to see it's got like a dual nature. The purpose is to govern systems and assemblies used for structural fire resistance.
Okay, holding the building up.
Right. And also for fire resistance rated construction. So it's not just about slowing the fire down. It's really about two separate functions working together.
So when we're studying this, we need to recognize those two distinct roles. First, structural integrity, the column, the wall, whatever it has, to resist, collapse under heat for, say, 2 hours.
Yep. Hold its load.
And second, containment, it has to stop the fire, the smoke, the dangerous heat from getting into the next space.
That's the critical insight. Fire safety pros often talk about integrity, basically. The structure staying put, no holes forming, and insulation, which is stopping the unexposed side from getting dangerously hot.
Right. So it doesn't just ignite things in the next room through the wall.
Exactly. And this chapter regulates both. The main goal, like it says, is to safeguard against fire and smoke spread within the building. And this is key to protect adjacent buildings, too.
And that bit about adjacent buildings, that immediately tells you why Section 705 on exterior walls is such a massive part of this chapter.
Absolutely. The rules change dramatically based on how close you are to that property line. The code recognizes that protecting the community from your building fire is just as vital as protecting your own occupants.
Makes sense. Okay, moving quickly to Section 702, multiple use assemblies. It's a short section, but I can see how this could be a common trip up in design. One wall having to do multiple jobs.
It's quick, but definitely essential to flag. The core idea in 702.1 is simple. If an assembly has to do more than one job, and that's super common these days, right? High-performance buildings.
Yeah, energy codes, sound codes.
Right. So if it has multiple jobs, it has to meet all the requirements for each job, no compromises.
Can you give a quick example? Where does that bite you in practice?
Sure. Think about a wall between two apartments. It probably needs to be a 1-hour fire partition, right?
Yeah.
Chapter 7 says so. But maybe Chapter 12 also says it needs a certain STC rating for sound control.
Okay, sound and fire.
Now, often making it better for fire adding dense materials also helps the sound rating. But what if that wall also has, say, a pipe going through it?
Penetration.
Exactly. The fire stopping you use for that penetration, it has to maintain the fire rating, obviously, but you also have to make sure it doesn't create an acoustic leak, ruining your STC rating. You can't just slap some fire caulk on and call it good. It has to meet the fire rules and the sound rules.
So it's the classic situation. You always have to meet the toughest requirement for any given characteristic.
That's it in a nutshell. If one part of the code says level X and another says level Y, your assembly has to hit the higher bar.
Okay, here's where the rubber meets the road. Section 703, fire resistance ratings and fire tests. If a wall says 2-hour rated, how do we actually know that? How that rating is established according to 703.1?
Right. 703.1 sets the foundation. There are basically three main ways to prove compliance. The most common, the most direct, is through test results. That's section 703.2.
Actual burning things.
Pretty much. Second, you've got analytical methods. That's 703.2.2 or 703.3, using calculations and known material properties. And third, there are approved alternate methods, section 104.11, which lets the building official approve other ways, maybe innovative stuff or ratings from older codes.
Let's stick with the tested assemblies for a minute, under 703.2. When we see that rating, where did it likely come from? What tests are we talking about?
The main standards for fire resistance ratings are ASTM E119 or UL 263. These are big standardized tests. They literally build a full-scale assembly, a wall, a floor, a column, stick it in a furnace, and cook it according to a very specific time-temperature curve.
Wow.
And the test isn't just about how long it stands up. It also measures if it stops too much heat getting to the other side, the unexposed side, because that heat could ignite stuff in the next room.
So what counts as failure in these tests? It's not just when the wall falls over, is it?
Oh, absolutely not. There are three main ways to fail an E119 test. First is structural failure.
Okay.
Yeah, collapses or can't hold its load. Second is integrity failure, cracks or openings form that let flames or hot gases through.
Okay.
But the third one, and this is often the limiting factor, especially for partitions, is temperature failure. That's when the average temp on the unexposed side rises more than 250 degrees Fahrenheit above the starting temp, or any single spot gets hotter than 325 degrees F above ambient.
Why that specific temperature?
Because that's roughly the point where common materials on the safe side, wood, paper, textiles, are likely to just spontaneously ignite from the heat radiating through.
That distinction, integrity versus temperature, seems really important to grasp. Now, what about tricky assemblies? Section 703.2.1.1 talks about non-symmetrical wall construction.
Yeah, this is a great example of the code forcing you to think worst case. If a wall is built differently on each side, maybe insulation on one, not the other, or one side faces a higher risk.
Like a corridor wall versus an apartment wall.
Could be. The rule is you have to test it with the least fire-resistant side facing the furnace fire, and the final rating you get. It's the shorter time achieved from testing both sides, or just the weak side if it's obvious.
So you can't just test the strong side and claim that rating.
Nope. Eliminates that kind of wishful thinking in fire design.
Then there's this complex language in 703.2.3 about restrained versus unrestrained assemblies. What does that mean practically?
Okay, this gets into how the assembly is actually connected to the main building structure and how it behaves when it gets hot. Things expand when heated, right?
Right.
So an assembly is considered restrained unless the designer or the test data proves it qualifies as unrestrained. A restrained assembly is connected in a way that stops it from freely expanding or rotating when heated. Think of a floor slab locked tightly into perimeter beams.
Okay, it's held tight.
Right. That restraint can actually help it achieve a higher fire rating sometimes because the expansion creates compressive forces that can help hold things together.
And unrestrained.
That would be like a floor section just resting on supports, free to expand and move in the furnace. Now, being restrained can help, but it can also cause failure if the material crushes or spalls under that expansion pressure. It's complex, and the code says you have to verify which condition applies based on the test data.
Got it. And 703.2.1.5 mentions extra checks for exterior bearing walls.
Yeah, for those, besides the standard E119 criteria, you also have to specifically check for that unexposed surface temperature rise and make sure it doesn't ignite cotton waste placed against it. It's an older method, but it double-checks that hot gases aren't leaking through in a way that could ignite adjacent materials, unless the assembly already way outperforms the basic E119 requirements for that duration.
Okay, what about the alternatives to actually burning stuff? The analytical and alternate methods in the 703.2.2 and 703.2.3.
Analytical methods are powerful. It means you can determine fire resistance using calculations based on known material properties, engineering analysis, or using standard designs from approved sources like ACI for concrete or ASI for steel.
So decades of testing have given us reliable data.
Exactly. We know how certain thicknesses of concrete or gypsum perform pretty predictably. So if your assembly matches the recipes later in Section 721 or meets the calculation rules in 722, you often don't need a new test.
And the approved alternate method?
That's basically Section 104.11, giving the building official the authority to approve other established or even innovative methods if they're shown to be equivalent. It allows for flexibility.
Moving to materials themselves, 7.3.3 covers non-combustibility. This seems crucial, especially for Type 1, Type 2, Type 3, and Type 4 construction, right? Those need non-combustible materials.
Absolutely critical. To be officially non-combustible, a material has to pass specific tests mentioned in Chapter 6. Section 703.3.1 points to two main tests. The primary one is ASTM E136.
What does E136 involve?
It's an internal material test. You basically put a sample of the material in a hot furnace and see if it burns, smolders, or significantly raises the furnace temperature, basically. Does it add fuel to the fire?
Okay, simple burn-a-burn test.
Pretty much. The other standard mentioned, mainly for exterior materials, is ASTM E26502. This one looks more at surface burning characteristics. To pass, it needs a flame spread index no more than 25 and a smoke developed index no more than 450.
What's the practical difference between E136 and E26522 for someone studying?
Think of E136 as testing the core material. Will the stuff itself burn? E2652 is more about the surface. Even if the core material is non-combustible, maybe a coating or facing could spread flame rapidly across the outside of the building. E2652 checks for that facade fire spread risk.
Got it. And 703.4 covers fire resistance rated glazing, windows and firewalls.
Yeah, if glazing is part of a rated assembly, it has to be tested to the same standard as the assembly itself, E119 or UL263. Regular glass breaks almost instantly in a fire. Fire-rated glazing is special stuff layers of glass, sometimes with intumescent gels between them designed to hold integrity and limit heat transfer.
Okay, before we leave 703, let's talk identification 703.5. How does an inspector know they're looking at a rated wall, especially years later?
That's exactly why 703.5 exists. Firewalls, fire barriers, and fire partitions have to be permanently marked. Usually it's a label, a stencil, maybe a plaque, often above the ceiling or near the floor line, somewhere visible if you look for it.
Crucial for renovations or maintenance, I imagine.
Absolutely. And for the fire department, they need to know which walls are critical separations.
And finally, 703.6, penetrations. Probably the most common failure point in reality.
Definitely a huge area of focus. Any penetration pipes, ducts, cables going through a rated assembly has to be protected. Usually that means using an approved fire stop system, tested specifically for that type of penetration and that type of wall or floor.
And there's a specific rule here for firewalls in 703.6.1 about spacing openings.
Yes, for firewalls, openings need to be separated, at least 15 feet apart and not closer than 30 feet horizontally along the wall, unless they are specifically labeled like fire and/or smoke barrier protect all openings. It forces designers to spread out the weak points in that ultimate separation.
All right, section 704. Now we're shifting from the walls containing the fire to the actual bones of the building holding things up during a fire. What's the main idea in 704.1?
Section 704.1 basically says that the structural members, columns, beams, trusses need fire resistance if they are supporting something that requires a fire resistance rating.
So if a beam holds up a 2-hour rated floor,
that beam needs to have a 2-hour rating too. Makes sense, right? The support can't fail before the thing it's supporting.
logical. Let's get into the details for steel protection in 704.6. Steel is strong, but famously loses strength fast when heated. So how must it be protected? What about continuity in 704.6.1?
The protection, typically concrete encasement, special gypsum board, or sprayed fire-resistant material, SFRM, has to cover the entire member, full distance. If it's an I-beam, the whole I needs to be covered.
Any exceptions?
The only minor allowance is that the protection can stop 12 inches from the edge where an attachment is hollow, like near a connection plate, but otherwise it's got to be continuous.
And 704.6.2 mentions reinforcement for the protection itself. What's that about?
That's all about durability, especially for spray-applied stuff, the SFRM. It can be kind of fragile, easy to damage during construction or later maintenance. So the code requires metal ties or mesh, sometimes called lath, embedded about ½ an inch into the spray material.
So hold it together.
Exactly. It helps resist impact and keeps the fireproofing from just falling off if it gets bumped or during the fire itself.
Okay, here's one I bet causes issues. 704.6.3 Embedded members. Can you run conduits or pipes inside the fireproofing?
Ah, yeah, that's a huge no-no and a critical inspection point. You absolutely cannot embed pipes, wires, conduits, ducts, whatever, in the required fire protective covering of a structural member.
Why not?
Because that fireproofing, especially the sprayed-on kind, relies on its continuous thickness for insulation. Every pipe or conduit embedded in it creates a path for heat to get to the steel faster, or a weak spot where the fireproofing might fall off.
So what's the solution if you need to run services along a column?
Keep them outside the required fireproofing layer. Or if the member is fully encased in something robust like concrete, then maybe it's allowed, but you can't just cut into the spray-on stuff. The simplest way is keep services separate from the thermal barrier.
Makes sense. What if the column is somewhere it might get hit, like a loading dock? That's 704.7 impact protection.
Right. If the fire protection is vulnerable to damage, say from forklifts or cars, it needs to be protected. Usually with a bollard or a guard post or maybe a concrete curb, up to a height of at least 5 feet.
To prevent the fireproofing getting scraped off.
Exactly. Interestingly, there's an exception saying specific corner guards aren't required in parking garages, as long as the protection is otherwise adequate.
Okay, let's quickly clarify the hierarchy. 704.2 for columns, 704.3 for the primary structural frame.
Right. Columns need continuous protection, basically from the foundation up to whatever they support above. The primary structural frame, that's the main columns, girders, beams, trusses supporting floors, roofs, or major walls, they generally need individual protection on all sides.
Why individual protection?
So the failure of one piece doesn't immediately bring down the whole system. It maintains some redundancy.
And secondary structural members, 704.4. They're less critical.
Slightly less stringent, yeah. These are things like infill beams just holding up a bit of floor or a non-load-bearing wall. They still need a rating, according to 703, but they might be allowed to rely on the protection from a fire-rated ceiling assembly below them, rather than needing individual encasement like the primary members often do.
Section 704.4.1 mentions light frame construction. How does that work?
In light frame, like wood or steel stud walls, the studs or columns inside the wall get their fire rating from the membrane protection, usually the layers of gypsum board on the outside. The drywall protects the studs.
And 704.4.2 covers horizontal assemblies, like those protective ceilings.
Yeah, if you're using a ceiling membrane like a suspended grid ceiling with rated tiles to protect the floor or roof structure above, that ceiling has to be installed exactly according to its listing and Section 711 requirements to actually provide that rating.
Okay, last big topic in 704, sprayed fire-resistant materials, SFRM, in 704.13. Very common material, but tricky to apply right.
Extremely common, and yes, application is critical. Section 704.13.4 says it must be applied according to the listing minimum thickness, minimum density. But the real key, maybe the most important part for inspectors, is 704.13.3, substrate condition.
Meaning the steel surface it's sprayed onto.
Exactly. The steel has to be clean, free of oil, dirt, loose rust or scale, any contamination. If the surface isn't properly prepared, the SFRM won't bond correctly.
And then it just falls off.
It can, yeah. Either during construction or worse, during a fire when the adhesion fails under stress. Then the steel is unprotected. Bad adhesion is probably one of the most common defects found with SFRM.
All right, Section 705, exterior walls. This feels like one of the most critical sections, especially regarding how buildings interact with each other. And it all revolves around this concept of fire separation distance, or FSD.
FSD is everything in this section. It's the distance measured from your building's exterior wall face to the closest property line, or maybe the center line of a street, or an imaginary line between buildings on the same lot.
And Table 705.2 starts by linking FSD to how much things can stick out.
Yeah, it limits projections like balconies or roof overhangs based on the FSD. Basically, the closer you are to the line, the less you can project out, and the more fire protection you'll likely need on the wall itself.
Which brings us to 705.3, linking FSD directly to the wall's required fire resistance rating. How does that work?
It's a direct relationship. Exterior walls need a fire rating based on two main things: the FSD and the building's type of construction from Chapter 6, Type 1, Type 2, etc. The general rule is if your FSD is less than, say, 5 feet, you almost always need at least a 1-hour rated wall, sometimes more, depending on occupancy.
And that rating protects your building from a fire next door, or protects the neighbor from your fire.
Both, really. But primarily, it's about protecting the adjacent property or preventing fire spread from your building to the neighbor. It maintains separation.
Okay, and 705.3.2 has rules for balconies and projections based on height.
Right. Balconies, decks, things sticking out from the wall, the materials they're made of are regulated based on the construction type and how high up they are. For instance, in non-combustible construction types, 1 and 2, if you're several stories up, those projections usually have to be non-combustible too, or maybe fire-retardant treated wood.
To stop fire climbing up the outside using balconies as fuel.
Exactly. If vertical fire spread up the facade is a major concern.
Let's quickly touch on 705.6, structural stability, and 705.7, unexposed surfaces.
Sure. 705.6 just reinforces that if the exterior wall needs a rating, any structural elements within that wall, like columns carrying load, also need to maintain their required rating as part of the wall assembly.
And 705.7, unexposed surface temperature.
That brings back the insulation criteria from the E119 test. For rated exterior walls, you have to limit the temperature rise on the inside surface. Again, prevents ignition of interior contents just from heat conducted through the wall.
Okay, now we hit what you call the navigational heart of 705. Openings in exterior walls, section 705.8. This sounds like peak exam territory.
Absolutely. If you need to know about windows and doors and exterior walls, this is your go-to. Section 705.8.1 and the crucial table 705.8 determine the maximum allowable area of openings, both unprotected and protected, in an exterior wall.
And what determines that allowable area?
It's based on that triple crown of code factors.
Yeah.
The fire separation distance, FSD, the building's construction type, and the occupancy group.
Let's really focus on table 705.8 for a second. How should someone approach using this table effectively?
Strategy 1. Always find your FSD first. Look down the left column. If you're really close, say 0 to 3 feet or 3 to 5 feet, you'll see immediately that for most construction types and occupancies, the allowable percentage of unprotected openings is 0 or very, very small.
Okay, close distance, minimal unprotected openings.
Right. As your FSD increases, say 5 to 10 feet or 10 to 15 feet, that allowable percentage of unprotected openings starts to go up. Maybe it's 15%, maybe 25%, maybe 45%, depending on the construction type and occupancy.
And if you're far away, like 30 feet or more?
If you're 30 feet or more out, generally, the wall itself doesn't even require a fire resistance rating based on FSD, and the amount of unprotected openings is usually unlimited by this table. So FSD is the king. Then construction type and occupancy, fine-tune the percentage allowed within that FSD range.
So say the table tells me I can have 25% unprotected openings, but my design needs 40% window area. What do I do?
Okay, good question. That means the extra 15%, 40% total, minus the 25% allowed unprotected, must be protected openings. And Section 705.8.2 tells you that protected openings have to comply with Section 716.
Meaning fire-rated windows or doors?
Exactly. Fire-rated assemblies. Section 705.8.3 notes that even unprotected openings still need to meet basic material rules from Chapters 24 for glass and 26 for plastics.
What if you want to mix some rated, some unrated windows at 705.8.4 mixed openings?
You can do it, but it involves a calculation. There's an equation in the code, essentially lets you trade area. You can convert the area of your protected openings into an equivalent, smaller area of unprotected opening, because protected openings are safer. You add that equivalent area to your actual unprotected area, and the total equivalent unprotected area must stay below the limit from table 705.8.
A bit complicated, but logical. It gives you credit for using safer openings.
Precisely.
And 705.8.5 covers vertical openings, specifically separating windows floor to floor. This is about preventing fire spread up the outside, right?
It's absolutely critical for multi-story buildings. If window openings on different floors are vertically aligned and not separated by enough solid wall walls, the spandrel space fire can break out a window on one floor and easily enter the window right above it.
So how does the code stop that?
If the vertical separation is less than 3 feet, you generally need either the wall section between them, the spandrel, to be rated for at least 1 hour, or you need to install a horizontal flame barrier. This is typically a non-combustible projection sticking out at least 30 inches from the wall, right between the openings. It acts like a shelf to deflect flames away from the window above.
Clever. Okay, wrapping up 705, joints 705.9, and parapets 705.11.
Right. 705.9 deals with the joint where the exterior wall meets the floors. That joint needs to be protected, usually with a fire-rated system, to stop fire sneaking through that crack. It's similar to the penetration rules.
And parapets, those little walls extending above the roof.
Yes, parapets are required on exterior walls when the FSD is very small, typically 3 feet or less. They have to extend a certain height above the roof and be made of non-combustible materials. Their job is to stop a fire on your roof from easily spreading horizontally over to your neighbor's roof right next door.
Okay, now we get into the big separators. Section 706, firewalls, versus Section 707, fire barriers. People use these terms interchangeably, but in the code, they're very different beasts, aren't they?
Worlds apart. Let's start with firewalls. Section 706. Think of these as the ultimate heavyweight separation. Their main job, 706.1, is to provide a complete separation, running from the foundation all the way to or through the roof, effectively creating two separate buildings side by side.
Two buildings. Legally.
Yes, for code purposes like calculating allowable area or determining construction type requirements, the firewall allows you to treat the structures on either side as independent.
And that leads to the defining characteristic of a firewall. Structural stability in 706.2.
This is the absolute key difference. A firewall must be designed and built so that if the entire building on one side collapses in a fire, the firewall itself remains standing, protecting the other side. It has to have structural independence. Think of it as needing to survive its neighbor falling down. It's designed according to NFPA 221.
Wow, that's a serious wall. What about ratings and materials?
Materials generally have to be non-combustible. The required rating, usually 2, 3, or 4 hours, depends on the occupancy groups being separated. You find the specific requirement in Table 706.4. High hazard occupancies, like Group H, often trigger that 4-hour requirement.
And continuity 706.4. It has to be truly continuous.
Absolutely. From foundation, through all floors, up to or through the roof, and it needs to tie into the exterior walls properly. It cannot stop short. There's a limited exception allowing termination at the underside of a rated roof deck in certain construction types 1, 2, or 3 if the rating is 2 hours or less, but the structural stability part must still be maintained.
How does it connect to the exterior wall? 706.5. Does it just stop flush?
No, that would let fire wrap around the end. The firewall usually has to extend out beyond the exterior wall face for a certain distance, or have T or L-shaped returns, or the intersecting exterior walls need to be protected near the firewall. This prevents fire from just jumping the gap at the corner.
Okay, that's firewalls, the ultimate divider. Now, Section 707, fire barriers. How are they different?
Fire barriers are about compartmentalization within a single building. They aren't creating separate buildings. Their job is to enclose specific high-risk areas or critical life safety elements.
Like what?
Common uses are enclosing exit stairways, elevator shafts, separating different occupancy groups within the same building, especially hazardous ones like Group H from others, or creating horizontal exits. They protect escape routes and contain specific hazards.
And the big structural difference, they don't need to survive a collapse.
Exactly. A fire barrier needs to maintain its own fire resistance rating for the required time, but 707.5 just says it needs to be supported by construction that also has at least the same fire rating. If the floor beam holding up the barrier fails, the barrier can fail with it. That's okay because it's all within one building's overall safety plan.
What are typical ratings for fire barriers?
Materials depend on construction type again. Ratings, found in Table 707.3, typically range from 1 hour up to 4 hours. A standard stair shaft might be 2 hours. Separating a high-hazard H1, H2, or H3 occupancy usually requires a 3-hour barrier, but some occupancy separations might only need 1 or 2 hours.
And openings. Any special rules for doors or windows in fire barriers? 707.6.
Yes, openings need to be protected with rated assemblies, just like firewalls, following Section 716. But fire barriers have an additional restriction. The total aggregate width of all openings is limited to 25% of the barrier's length.
Why limit the opening so strictly?
To maintain the integrity of that compartment, especially when protecting something vital like an exit stairway, you don't want too many potential failure points, doors, windows, breaching that protective enclosure.
Okay, let's step down the hierarchy to the more common interior separations. Section 708, fire partitions. Where do we typically find these?
Fire partitions are your standard workhorse for interior separation. They're used for things like separating individual tenant spaces in a mall, separating apartment units or hotel rooms, sleeping units, and very commonly they form the walls of exit corridors. See 708.1.1 through 708.1.5 for the list.
And how do their ratings compare to fire barriers? Less robust.
Generally, yes. Fire partitions typically have lower ratings, most often 1 hour. Sometimes even just a half-hour rating is permitted, for example, between sleeping units in non-combustible Type 1 and Type 2 buildings.
What about continuity? Do they have to go slab to slab like barriers often do?
Not always. Section 708.4 covers continuity. They generally need to extend from the floor slab below to the ceiling or roof slab deck above. However, there's a common exception. They can often terminate at the underside of a fire resistance rated ceiling assembly if that ceiling has a rating at least equal to the partition rating.
So a 1-hour partition can stop at a 1-hour rated ceiling grid.
Correct. That's a very common construction method, especially in office buildings or hotels. But the ceiling has to be properly rated and installed.
Okay, next level. Section 709, smoke barriers. The name says it all focus shifts to smoke.
Exactly. Smoke barriers are specifically designed to limit the movement of smoke. You find these primarily in places where evacuating everyone quickly is difficult, and defending in place is part of the strategy. Think hospitals, nursing homes, group I occupancies.
Do they also need a fire rating?
Yes, that's a key point. Section 709.3 usually requires smoke barriers to have a minimum 1-hour fire resistance rating in addition to their smoke stopping capabilities. There are some exceptions, particularly in Group 1, Condition 2, like hospitals, where if the surrounding construction provides enough protection, the barrier itself might not need the fire rating, but it must restrict smoke passage.
So fire resistance plus smoke tightness.
Right. And continuity, 709.4, is usually slab to slab. Openings, 709.5, need protection per Section 716, but critically, the doors must have specific gaskets or seals to stop smoke leakage and usually need to be self-closing or automatic closing.
Okay, and the final type, Section 710, smoke partitions.
Yeah.
Even less restrictive.
Correct. Smoke partitions are purely about limiting smoke transfer. Section 710.3 clearly states they are generally not required to have a fire resistance rating.
So where would you use these?
Often in places like corridors leading to elevator lobbies in some situations, or other areas where you want to slow down smoke movement but don't need the full hour of fire protection that a smoke barrier provides.
Since they don't have a fire rating, their effectiveness must hinge entirely on how well they seal openings, especially doors.
Absolutely. And that's where 710.5.2.2 comes in, detailing smoke and draft control doors. This is a really important detail for exam study. These doors, even without a fire rating themselves, must meet specific air leakage standards.
Which standards are those?
They need to be tested according to UL 1784 and comply with NFPA 105. The key performance metric is limiting air leakage to no more than 3.0 cubic feet per minute per square foot of door area when tested under pressure. That tight seal is what makes them effective smoke partitions, even without an hourly fire rating.
Right, let's shift from vertical separations to horizontal ones. Section 711 covers floor and roof assemblies. When do these horizontal planes need a fire rating?
According to 711.2, horizontal assemblies need a fire resistance rating primarily when they're separating different zones for safety. Think separating individual apartment units from each other, floor to floor, or separating different occupancy groups stacked vertically, or enclosing hazardous incidental use areas like boiler rooms or storage rooms below occupied spaces.
And what's this about an unsafe concealed space in 711.2.6? That
Yeah.
sounds ominous.
It is. If you have a hidden space, like an attic or the space above a dropped ceiling, a plenum, and it's considered unsafe, maybe it's not properly fire blocked, doesn't have sprinklers, or contains risky materials, the code might require the floor or roof assembly above that unsafe space to have a 1-hour fire resistance rating.
To basically contain a fire that might start in that hidden unsafe area.
Exactly. It's a protective layer.
Okay, now Section 712, vertical openings. You mentioned earlier these are like chimneys for fire and smoke.
They really are. And the fundamental rule, 712.1.1, is crystal clear. Vertical openings connecting stories, think stairwells, elevator shafts, escalators, dumbwaiters, must be enclosed by fire resistance rated shaft enclosures built according to Section 713, unless, of course, a specific exception applies.
Why is enclosing them so non-negotiable?
Because fire and smoke rise naturally and rapidly. An unprotected vertical opening is a guaranteed pathway for fire to spread instantly from floor to floor, compromising the entire building's safety and egress system.
What are some of the key exceptions? 712.1.3 through 712.1.7, where you don't have to enclose them. These must be pretty limited.
They are limited and usually rely heavily on other compensating safety features, like sprinklers. Some examples include maybe an escalator connecting just 2 floors in a sprinklered building, if it has special draft curtains and extra sprinklers around the opening, or maybe an unprotected opening connecting only 2 levels within a single apartment unit.
What about big open spaces like atriums?
Atriums are a major exception, covered in detail in Section 404. They allow large, multi-story open spaces, but they come with a whole suite of mandatory safety systems, full sprinkler protection, sophisticated smoke control systems, limits on what activities can happen in the atrium, etc. It's a Complex trade-off.
And 712.1.13 mentions horizontal fire resistance for large openings.
Yeah, if you have very large openings in floors, they might need to comply with a specific test standard, NFPA 288, for horizontal fire door assemblies, and the floor assembly itself must maintain its required rating.
Section 713 dives deeper into those shaft enclosures we just mentioned. What determines the fire rating needed for a shaft wall?
The main factor, outlined in 713.4, is how many stories the shaft connects. If it connects 4 or more stories, it needs a 2-hour fire resistance rating. If it connects fewer than 4 stories, a 1-hour rating is generally required.
Why the difference? More stories, higher risk.
Exactly. More stories means potentially more people needing more time to evacuate and a greater potential fire load. So the enclosure protecting that vertical path needs to be more robust.
And continuity, 713.5, is obviously critical for a shaft.
Absolutely flawless continuity is required. Shaft walls must run continuously from the lowest floor slab they penetrate up to the underside of the roof slab or deck.
Oh.
Any openings into the shaft for doors, vents, access panels must be protected with appropriately rated assemblies per Section 716 to maintain the integrity of that enclosure. See 713.7.
This section also calls out specific rules for waste and linen chutes in 713.13, requiring compliance with NFPA 82. Why the extra attention for chutes?
Because chutes are inherently risky. They often contain flammable materials, trash, laundry. People sometimes improperly discard burning items like cigarettes down them, and they provide a direct vertical path for fire spread. NFPA 82 has specific requirements for chute construction, self-closing doors at inlets, sprinkler protection inside the chute sometimes, and discharge room protection.
Makes sense. Okay, Section 714 brings us back to penetrations, but maybe focusing more broadly now, protecting rated assemblies from anything poking through them.
Yes, this section is all about maintaining the integrity of fire resistance rated walls, floors, and ceilings when things like pipes, conduits, wires, ducts, or even joints pass through them. It's where the fire separation often fails if not done correctly.
So 714.3 covers fire resistance rated penetrations. What's the key requirement?
The key is that penetrations through rated assemblies must be protected by an approved fire stop system, and that system must have been tested according to specific standards, usually ASTM E814 or UL 1479.
What do those tests do?
They simulate a fire. They put the fire stop system, the caulk, putty, collar, wrap, whatever it is, around the penetrating item in a section of wall or floor and subject it to the standard fire test curve. The system has to prevent flame passage and limit heat transfer through the opening for the required rating period, the F rating and sometimes the T rating.
Okay, let's clarify membrane penetrations again, 714.4. This is when something only pokes through one side of a rated assembly, like the drywall on one side of a rated stud wall.
Exactly. This applies to walls or ceilings where the membrane itself, the gypsum board, for example, is contributing to the fire rating. If you put an electrical box or a small pipe just through that membrane on one side.
Does it still need protection?
Yes. The opening needs to be sealed, often with fire-rated putty pads or sealant. But critically, there's also a limit on the total area of these membrane penetrations. The rule of thumb is a maximum of 100 square inches of openings within any 100 square feet of wall or ceiling area.
That 100 in 100 rule seems like a really important takeaway. You can't just pepper the wall with electrical boxes, even if they're sealed.
Correct. Too many penetrations, even if individually sealed, can compromise the overall performance of that membrane layer. We should also note, again, there's a calculation method, equation 714.2, that can be used for walls to potentially allow more area if specific temperature criteria are met, but the 100 and 100 rule is the simpler, more common limit to remember.
And 714.5 confirms that penetrations through horizontal assemblies, floors, and ceilings follow similar rules. Tested systems, rated appropriately.
Yes, the principles are the same. Use a list and fire stop system, E814UL 1479, suitable for the type of floor construction, and the specific penetrating item plastic pipe needs a different system than a metal conduit, for instance.
All right, moving on. Section 715 deals with joints and voids. This isn't about pipes poking through, but about the seams where different building elements meet.
Exactly. Think about the gap between the edge of a floor slab and an exterior curtain wall, or a control joint designed into a long concrete block wall. These joints create potential pathways for fire and smoke.
So how are they protected?
Section 715.3 requires these joints in or between fire resistance rated assemblies to be protected by an approved fire resistance rated joint system.
A joint system, like fire caulk.
It can be specialized fire caulk, yes, often used with mineral wool backing, but the key is that these systems often need to accommodate movement. Walls and floors expand and contract with temperature changes or move during seismic events.
Ah, so the joint protection has to be flexible, but still fire rated.
Precisely. That's why 715.3.3 requires these joint systems to be tested according to standards like ASTM E 1966 or UL 2079. These tests include cycles of movement during the fire exposure to make sure the sealant doesn't tear or pull away, maintaining the fire barrier even while stretching or compressing. It's pretty rigorous.
Okay, now section 716, opening protectives. This is the big section on fire doors and fire windows, right? Making sure the hole you put in your rated wall is also protected.
Absolutely. This is where you find the requirements for the doors, windows, shutters, and even glazing used within those openings. 716.1.1 just reiterates that ratings can come from tests, analysis, or alternate methods.
Let's talk about marking and ratings in 716.1.2. There are all these letters W, H, D, T, O, X. What do they mean? Table 716.11 point.
Yeah, those letters on the label of fire-rated glazing or doors are crucial for inspectors and designers. They tell you what criteria the product met during testing. W means it met the full wall assembly criteria, resist fire like a solid wall, including limiting heat transfer, important for firewalls. H means it withstood the hose stream test, getting blasted with water after the fire exposure, simulating what firefighters do. It tests impact resistance. D means it met criteria for doors. T means it met the temperature rise limitation on the unexposed side, critical for stairwell doors. O means it's suitable for openings. X might indicate other conditions. Understanding these helps ensure you're using the right product for the right location.
Okay, that's helpful. And table 716.1D is the main lookup for finding the required rating for a door or window based on the wall it's in.
That's your primary quick reference. You find the type of assembly the opening is in firewall, fire barrier, fire partition, shaft enclosure, corridor wall, exterior wall based on FSD, and the table tells you the minimum required fire protection rating in hours or minutes for the door or window assembly.
Give me an example. A 2-hour rated stair enclosure shaft.
Look up shaft enclosure, 2-hour rating in the table. It will typically point you to needing a 1.5-hour, 90-minute rated fire door assembly.
Notice it's often less than the wall rating. A 2-hour wall gets a 1.5-hour door.
Yes, that's common. Fire door testing, NFPA 252, is slightly different than wall testing, and historically, a slightly lower rating on the door was accepted as providing equivalent protection for the opening within the higher rated wall. A 3-hour door is typically the max you'll find, used in 4-hour walls. A 1-hour partition usually gets a 1-hour door, though sometimes less, like 45 or 20 minutes, depending on the specific application, like corridors.
Okay, for fire doors themselves, 716.2, tested to NFPA 252. What about glazing within the doors or a size limit?
Yes, a very important one to know, especially for exams. Section 716.2.5.1 puts strict limits on the size of fire resistance rated glazing, the kind that blocks heat, not just fire. Indoors located in walls rated higher than 1 hour, like firewalls, barriers, shafts. The maximum size is limited to 100 square inches.
Only 100 square inches. That's pretty small, like a small vision panel.
Exactly. It ensures that even if that high-performance glazing eventually fails, the resulting hole is relatively small, limiting fire spread. Fire protection-rated glazing, which mainly just stops flames, not heat, might be allowed in larger sizes in lower-rated assemblies, like 1-hour partitions.
In fire window assemblies, 716.3, tested to NFPA 257 or UL9.
Right. These are typically window units designed to be installed in fire-rated walls. Their ratings, per table 716.13, usually range from 20 minutes up to maybe 1.5 hours, depending on the wall they're in. A key point in 716.3.2 is about non-symmetrical glazing in exterior walls. It generally needs to be tested from both sides unless protected to handle both internal and external fire exposure.
Okay, section 717. This tackles how HVAC systems ducts carrying air penetrate rated walls and floors without compromising the separation. Let's start with fire dampers. 77.3. Where are these required?
Fire dampers are basically required whenever a duct penetrates a fire resistance rated assembly like a fire barrier, fire partition, shaft wall, or floor assembly, unless a specific exception is met. They're designed to automatically close and block the duct in case of fire.
How do they activate? Heat.
Typically, yes. Most standard fire dampers have a fusible link, a piece of metal designed to melt at a specific temperature, usually 165 degrees F or 212 degrees F. When it melts, it releases spring-loaded blades that slam shut, sealing the duct.
And how is the damper's rating determined? Does it match the wall rating?
Usually not exactly. Table 717.3.2.1 gives the rule. If the wall or floor assembly is rated less than 3 hours, you typically need a 1.5-hour rated fire damper. If the assembly is rated 3 hours or more, you need a 3-hour rated damper. The damper has to hold back fire long enough for the assembly itself.
Okay, that's fire dampers for heat. What about smoke dampers in 717.4? Where are they needed?
Smoke dampers are required where ducts or air transfer openings penetrate assemblies that are specifically designated as smoke barriers, Section 709, or sometimes smoke partitions, Section 710. Their job is to stop smoke movement through the ductwork.
How do they activate? Not heat, presumably.
Right. Smoke dampers are activated by smoke detection. They are linked to smoke detectors either in the duct, in the area, or tied into the building's fire alarm system. When smoke is detected, an actuator closes the damper blades.
And their rating, is it timed like fire dampers?
It's a bit different. Smoke dampers are rated based on leakage, Class 1 or Class 2, and their ability to operate under airflow and at elevated temperatures, usually tested to UL 555S. They need to close quickly and seal tightly against smoke, even before temperatures get super high. See 717.4.2.
Can you have a damper that does both, fire and smoke?
Absolutely. Combination fire-smoke dampers are very common, 717.3.3. They meet the requirements for both. They have a heat-activated release mechanism, fusible link, and they can be closed by a signal from a smoke detector. 717.3.3.2 mandates that they must close upon detection of smoke.
And critically, 717.4 mentions access and identification. You need to be able to inspect these things.
Yes, absolutely essential. Dampers are mechanical devices that can fail. They need to be accessible for periodic inspection and testing. The access door or panel in the ceiling or wall must be clearly labeled, something like fire smoke damper, so maintenance crews know it's there and what it is.
Finally, 717.5.3 discusses ducts running inside shaft enclosures. Are dampers always needed when a duct breaks out of a shaft?
Generally, yes, a fire damper or combination damper is needed where the duct penetrates the shaft wall. However, there are some important exceptions. For example, if you use rigid steel subducts extending a certain distance inside the shaft, or if the entire HVAC system serving that shaft is fully ducted and meets certain criteria, you might not need dampers at the shaft penetration itself. The idea is that the robust ductwork within the shaft provides the protection.
All right, let's look at some of the perhaps less obvious protection measures. Section 718 covers fire blocking and draft stopping. These are about stopping fire spread within hidden spaces, like inside walls or above ceilings.
Exactly. Concealed spaces, wall cavities, floor-ceiling joist spaces, attics can act like chimneys, allowing fire and smoke to spread rapidly unseen. Fire blocking breaks up these spaces into smaller compartments.
How is it done? What materials?
Fire blocking involves installing barriers vertically at floor and ceiling levels and horizontally at intervals, usually every 10 feet, within those concealed spaces. Section 718.2.1 lists acceptable materials, things like solid lumber, 2 layers of nominal wood, gypsum board, cement board, or even bats or blankets of mineral wool or fiberglass insulation, as long as they're held securely in place.
So just stuffing some insulation in the stud cavity works.
If it's listed as an approved fire-blocking material and secured properly, yes. The goal is just to stop the free passage of flame and hot gases through that hidden chase.
And draft stopping in 718.3, similar idea but bigger scale.
Kind of. Draft stopping applies mainly to large horizontal concealed spaces, like attics or the space above suspended ceilings and large floor areas. It requires dividing these large areas into smaller sections, typically no more than 1,000 square feet for attics, or aligned with smoke compartments below. It uses similar materials, often gypsum board or wood panels, to slow down the horizontal spread of smoke and fire across a large, open, hidden space.
Okay, Section 719 seems very specific. Fire resistance requirements for plaster.
Yeah, this section directly supports the prescriptive ratings found later in Section 721. It basically specifies the minimum required thickness for gypsum plaster or Portland cement plaster when it's being used as the protective layer contributing to a fire resistance rating. If Table 721 says you need plaster for a 1-hour rating, this section tells you how thick it needs to be.
Got it. And Section 720 deals with thermal and sound insulating materials. Does regular building insulation pose a fire hazard?
It certainly can, especially plastic foams or loose-fill cellulose. That's why 720.1 requires insulation materials to meet specific limits on flame spread and smoke development when tested, usually by ASTM E84 or UL 723.
What are the typical limits?
For most insulation installed in concealed spaces or non-rated assemblies, 720.3, the requirement is a maximum flame spread index of 25 and a maximum smoke developed index of 450.
The 25, 450 numbers. That sounds familiar.
It's the standard benchmark for a Class A interior finish material. It ensures the insulation itself won't significantly contribute to rapid fire growth or generate excessive smoke that could obscure escape routes. Specific types like cellulose or foam plastics might have additional requirements or need covering layers. See 720.3.1 and 720.3.2.
Okay, we've arrived at the real meat and potatoes sections for determining ratings. Section 721, prescriptive fire resistance, and Section 722, calculated fire resistance. Let's start with 721, the prescriptive or cookbook approach.
Section 721 is incredibly useful, especially for common construction types and for exam preparation. It basically provides pre-approved recipes for building elements, walls, floors, columns, beams that achieve specific fire resistance ratings, 1, 2, 3, or 4 hours, without needing further testing or complex calculations.
If your assembly matches the description exactly.
Exactly. You follow the recipe precisely. This section is filled with detailed tables.
Like Table 721.1, which covers protection for structural steel. How do you read that?
Table 721.1 gives minimum thicknesses of various protective materials, usually concrete, gypsum, or spray-applied fireproofing, needed to protect steel columns and primary trusses for different ratings. A key variable you'll notice is the type of concrete aggregate used for encasement.
Carbonate versus silicious. Why does that matter?
It matters a lot. It comes down to how the concrete behaves under intense heat. Silicious aggregates, which contain quartz, tend to spall more, meaning chunks can break off explosively when heated due to internal moisture turning to steam and differential expansion. Carbonate aggregates, like limestone, are generally more thermally stable and resist spalling better.
So you might need a thicker layer of silicious concrete than carbonate concrete to get the same fire rating?
That's often the case, yes. The table reflects this difference based on extensive testing. It's a great example of the deep material science behind these seemingly simple tables.
Okay, then there's the massive table 721.2 for walls and partitions.
Yeah, this table is incredibly detailed. It lists specific constructions for walls, various types of brick, concrete block, solid, grouted, ungrouted, clay tile, concrete, and many variations of gypsum board partitions on wood or steel studs. For each specific recipe, like item 11 to 1.1, a non-combustible stud partition with gypsum board, it tells you exactly what thickness of gypsum, what type, like type X, how many layers, the stud type and spacing, fastener details, everything you need to achieve a specific rating, say 1 hour or 2 hours.
So to follow to the letter.
Absolutely. Any deviation means the prescriptive rating doesn't apply, and you'd likely need to go to calculations or testing.
And table 721.3 does the same thing for floor and roof systems.
Correct. It provides prescriptive details for concrete slabs, thickness based on aggregate and restraint, steel joist systems with ceilings, wood joist systems, etc., again specifying materials and thicknesses needed for 1 to 4 hour ratings.
So Section 721 is great if your design fits a standard recipe. But what if it doesn't? That's where Section 722, calculated fire resistance, comes in.
Exactly. Section 722 provides methods to determine the fire resistance of building elements using engineering calculations based on material properties and established formulas, rather than just looking up a recipe. This allows for more design flexibility or justification of unique assemblies.
For example, 722.2 covers calculations for concrete walls.
Right. It provides formulas like equation 7 to 4 for multi-Y walls that let you calculate the theoretical fire resistance based on factors like the equivalent thickness of the concrete, the type of aggregate, and other properties. We're just noting the calculations exist here. We won't go into the math.
And similar calculation approaches exist for concrete slabs, 722.2.3, and columns, 722.2.4.
Yes, alongside tabulated minimum dimensions, there are calculation methods to refine the required thickness or cover based on heat transfer principles. Table 722.2.31 gives minimum slab thicknesses, for instance.
Let's talk about the calculation method for structural steel in 722.5. It introduces this concept of the weight to heated perimeter ratio, WD. This sounds important.
It's a fundamental concept for steel fire protection. 722.5.1.1. WON is the weight of the steel member per linear foot. Think of it as its thermal mass, how much heat it can absorb. D is the perimeter of the steel shape that's directly exposed to the fire.
So why is the WD ratio significant?
A steel member with a high WD ratio is relatively thick and heavy compared to its exposed surface area, like a massive column. It heats up more slowly because the heat has more mass to penetrate. Therefore, it needs less thickness of fireproofing material to achieve a given rating.
Conversely, a light, thin steel member, like maybe a joist.
Right. A light member has a low WD ratio. It has less mass relative to its exposed surface, so it heats up much faster and requires a thicker layer of fire protection to last the same amount of time in a fire. Tables 722.5.1, 1 through 4 provide WD ratios for common steel shapes. Then you use formulas like equation 713 for SFRM to calculate the required protection thickness based on that WD ratio and the target fire rating.
That really clarifies why different steel shapes need different protection thicknesses. It's not arbitrary.
Not at all. It's based directly on how quickly the specific shape will reach its critical failure temperature.
Finally, 722.6 provides calculation methods for wood frame assemblies. How does that work? Is it about char rate?
It's based on a component additive method.
Yeah.
You basically calculate the fire resistance by adding up the time contributed by each layer of the assembly. Table 722.6.21, for example, assigns specific minutes of fire resistance to different types and thicknesses of protective membranes, like gypsum board or plaster. You add the time for the membrane, potentially time for studs based on charring, maybe time for insulation to get the total calculated rating. Table 722.6.25 adds time for additional protection measures. Hashtag #Chagaspertine.
Outro.
Wow. We have covered a tremendous amount of ground navigating through IBC Chapter 7 fire and smoke protection features. It's definitely dense, but breaking it down section by section, you can really see the logic emerge. Absolutely. Once you understand the functional purpose of each part, it becomes much more manageable. So, to quickly recap the key takeaways, we looked at how ratings are established, Section 703, mostly testing. We focused on the crucial differences between firewalls, 706, creating separate buildings, needs structural stability, fire barriers, 707, compartmentalizing within a building, protecting egress hazards, and fire partitions, 708, standard tenant dwelling unit separation.
And we saw how exterior wall requirements, 705, are almost entirely driven by that fire separation distance, making Table 705.8 absolutely critical for figuring out allowable window and door openings.
Right. And then the two main paths to compliance. Section 721, the prescriptive cookbook, using those detailed tables your shortcut for standard designs and exams. And Section 722, the calculated route, using engineering principles like concrete properties or the WD ratio for steel, allowing for more customized solutions.
For anyone studying for an exam, what are maybe the top 3 things to really lock down from Chapter 7?
Okay, good question. First, definitely understand the functional difference between firewalls, fire barriers, and fire partitions. Second, know how to use Table 705.8 for exterior wall openings based on FSD. And third, grasp the basics of penetration protection, Section 714 fire stopping, and opening protection, Section 716 rated doors windows, and their ratings from Table 716.12. Oh, and maybe know that 100 and 100 rule for membrane penetrations.
That's excellent practical advice. Thank you so much for making this incredibly complex chapter feel much more clear and, well, navigable.
My pleasure. It's important stuff.
If this review has helped you understand Chapter 7 better, please consider supporting the Code Navigators. Helping us create future code content like this is easy. Just visit the Patreon link provided in the show description. Your support really does keep these detailed reviews going.
And maybe one final thought to leave you with. You look at Chapter 7, and it seems like just a massive list of rules, tables, and numbers. Prescriptive stuff. But remember, every single rule in here is ultimately rooted in the physics of fire thermodynamics, heat transfer, how materials actually break down under extreme heat.
Right, like the difference between carbonate and siliceous concrete.
Exactly. That tiny detail in Table 721 reflects real-world material science about spalling, or the WD ratio for steel that's pure engineering about heat absorption. So while you're memorizing the rules, remember they come from trying to understand and contain one of the most destructive forces we encounter. The code is the language we use to translate that science into safer buildings.
A really powerful way to think about it. It's not just arbitrary rules, it's applied science based on hard lessons learned. Fantastic. Until the next code section, everyone, keep your plans up to code.
And stay safe out there.